Dear students, the present lecture is on simple harmonic motion. I already delivered 2 lectures on simple harmonic motion. This is the third one and possibly the last one on this on simple harmonic motion. We have discussed free oscillations. Now today I am discussing how it's possible to combine 2 oscillations, and when a particle is under 2 motions along x-axis, along y-axis, we want to develop a relationship, an equation which will give us the resultant displacement of the particle when it is under 2 simple harmonic motions. So if a particle is under the action of a force which will oscillate it along the x-axis, a particle under the action of a force which will oscillate it back and forth along the x-axis. There is one more force along the y-axis, and this force will try to push the particle in the y direction, up and down. So what we want to do is that we want to develop a relationship which will tell us what is the shape, what is the figure the particle will move when it is under 2 oscillations, oscillation along x-axis and oscillation along y-axis. So in other words, we want to develop a relationship for the composition of 2 oscillations, one along the x-axis and other along the y-axis. So if I write down an equation for simple harmonic motion along x-axis, that is, if I write x is a1 sine omega t. This is the equation of simple harmonic motion along x-axis. And obviously this simple harmonic motion is created by a force that is proportional to displacement and directed towards this point O, let me suppose. And there is one more force that is along the y-axis that will make the particle to oscillate along the y direction. But now we have to see if the 2 forces are simultaneously present, what is the resultant motion of the particle? What is the figure in which the particle moves? Is it simple harmonic motion? Again, that we have to see. And the final answer will be given by the composite equation. So the particle moving along the y direction is given by y equal to a2 sine omega t plus phi. These are the 2 equations, one along the x-axis and other along the y-axis. And you see the particle when moves along the x-axis, it will move with an amplitude of a1. When the particle moves along the y-axis, it will oscillate with an amplitude of a2. But when either is present, when only either is present, other is absent. If the particle is under both the motions, means if the particle is under the 2 forces, one along x-axis, other along y-axis, we have to find its resultant motion. In other words, it is the composition of 2 simple harmonic motions which are at right angles to each other. So here the 2 equations differ by a phase of phi. The 2 equations differ by a phase of phi, means the 2 motions have a phase difference of phi. So if we combine these 2 equations and want to find the resultant equation, so from equation 2 one gets y by a2 y by a2 is equal to sine omega t plus phi. This equation I get from equation 2. So if I expand this equation, so what I get, so y by a2 is sine omega t cos phi plus cos omega t sine phi. This is simply an expansion of this according to rule of mathematics, sine of omega t cos phi plus cos omega t sine phi. Now this omega sine omega t can be substituted from here, from the first equation. And when we substitute it like this, it is y by a2 equal to x by a1 cos phi plus, what about cos omega t? Yes, cos omega t can be substituted in terms of sine omega t. and it can be root of 1 minus x square by a1 square sine phi. You please look at this equation very carefully. If we shift it from to the left and then square, we'll get this one. Is a y by a2 minus x by a1 cos phi. It will be equal to root of 1 minus x square by a1 square sine square phi. Sine phi. Sine phi. So carrying the equation we get. If we square the equation, we get like this. Y by a2 minus x by a1 cos phi square is just equal to 1 minus x square by a1 square sine square phi. If we rearrange the terms, we get this equation. It is x square by a1 square, x square by a1 square, x square by a1 square plus y square by a2 square minus 2 times xy by a1 a2 cos phi equal to sine square phi. This equation is obtained when we rearrange the terms, and if you look at this equation very carefully, it is the equation of an ellipse. It is the general equation of an ellipse. So this is the general equation of an ellipse. It is general equation of an ellipse, but the phi will determine the shape of the ellipse. The ellipse could be like this, it could be like this, or it could be like this. And the shape of the ellipse simply depends upon the phase difference between the two oscillations, that is x and y. So the conclusion is this: if the two oscillations, simple harmonic oscillations, are at right angles to each other with a phase difference of phi, the resultant motion of the particle will be a general ellipse. But again, it depends upon phase difference phi. Different phase difference between the two oscillations will make the shape of the ellipse different. And if we put phi is equal to pi by 2, means if we give this specific value to the phi, phase difference between the two oscillations, and if we put a1 is equal to a2, means the two oscillations move with the same have the same amplitude, then let us see what is the shape of the figure in which the particle moves under these two simple harmonic motions. Case number first. Case number first. If phi is equal to pi by 2 and a1 is equal to a2 is equal to a, let me suppose, I am giving a special value to the phase difference between the two oscillations which are at right angles to each other, and I have to see what's the shape of the figure in which the particle moves. What's the shape of the figure in which the particle moves? You see, x square by a1 square plus y square by a2 square minus 2xy by a1 a2 cos phi is equal to sine square phi. Putting phi is equal to pi by 2, this term will become 0 and this term will become 1. So here I will write x square by a1 square plus y square by a2 square is equal to 1. So employs x square by a square plus y square by a square is equal to 1. If you look at this equation very carefully, it becomes a square plus y, x square plus y square is equal to a square. We can recognize this equation. This is the equation of a circle. So that simply means if the two oscillations, perpendicular oscillations, if they are the same amplitude, the phase moves pi by 2, then the particle will move in a circle. This is the equation of a circle. This is the equation of a circle. But if the phase difference is, let me suppose, 0, and A1 is not equal to A2, then let me discuss the second case. The second case is case second. If A1 is equal to A2 is equal to case second, if phi equal to 0, let me suppose, in that case what will happen? It's x square by A1 square plus y square by A2 square minus 2xy by A1 A2 cos phi is equal to sine square phi. So it will become x square by A1 square plus y square by A2 square minus 2xy by A1 A2 is equal to 0, because this term is 1, this is 0. So in this case we can write it is x by A1 minus y by A2 whole square is equal to 0. That implies x equal to A1 by A2 y. What does this equation indicate? This equation indicates that a particle will move in a straight line because x and y are linear. So again, if the two oscillations are perpendicular to each other with a phase difference of 0, and then we say that the particle will move in a straight line with a slope of A1 by A2, and the particle is passing through the origin of the coordinate system. Case number 3. If phi is again pi by 2, if phi is again pi by 2 and x square by A1 square plus y square by A2 square minus 2xy by A1 A2 cos phi is equal to sine square phi. Let me substitute phi is equal to pi by 2. But here in this case, it is different from the first case, because there we supposed A1 is equal to A2. Here A1 and A2 are different. So it implies x square by A1 square plus y square by A2 square. It is 0 and it's 1. It is 0, it's 1 is equal to 1. If you look at this equation is simply the equation of an ellipse. It is equation of an ellipse. Now let me go to the damped oscillations. So what we have discussed is that when the two oscillations are at right angles to each other and their phase difference is phi, then the resultant motion of the particle will be a general ellipse. But under some special cases, it will move in a circle, and it will move in a special kind of ellipse if phi is pi by 2, and it can also move in a straight line if phase difference is what you call a 0. Let me go to the damped oscillations. Damped oscillations. We know when a particle oscillates back and forth in vacuum, it will oscillate forever, because there is no damping around. There is no medium around so that which can decrease its amplitude or which can suck out its energy. It will oscillate forever. Suppose a particle now, it is under the simple harmonic motion, or it is under the force of special force F is equal to minus kx, which will make the particle to oscillate back and forth. Let me suppose now there is a surrounding medium. The particle oscillates in a medium in air, in the medium of air, or the particle oscillates in the medium of Gilstein, or it may oscillate inside water. Then the surrounding medium drains out its energy, and after some time the particle will stop oscillating. So this is what you call as damped oscillations, a particle oscillating in a given medium. The surrounding medium will drain out its energy. So first of all, we have to see how to write down the equation for damped oscillations. We already know the equation of a simple harmonic free oscillations. So we have to add some damping term so that the total equation represents damped oscillations. But here physically we can understand that in damped oscillations, the particle amplitude will decrease, because particle amplitude is directly related to the energy. Once the energy is being sucked out from the system, once the energy is being sucked out from the object, the amplitude directly decreases, and after some time the particle will stop. So starting from the basic equation of simple harmonic motion, let's write F equal to minus kx. This is the basic equation of simple harmonic motion. But obviously these are free oscillations. And in order to write down the equation for damped oscillation, we have to write down a factor. We have to write down a factor which is responsible for the damping action. What is that factor? You know, when the particle oscillates back and forth in a given medium, if it's moving fast, the liquid or the surrounding medium will go fast over the object, so thereby creating more resistance. So the damping or the resistance offered by the surrounding medium should somehow be proportional to the velocity, because more the velocity of the particle, more the speed of the particle, more is the damping, more is the resistance offered by the liquid to the motion of the object. So somehow the damping force should be proportional to velocity of the object. So here we write F is equal to minus kx. So we have to write here the third term which is responsible for damping. So the obvious term must be minus b into velocity dx by dt, where b is a constant depending upon the medium. It may depend upon the density, viscosity, it may depend upon the properties of the medium. So this is the general equation for damped oscillations. So writing for f m d2x by dt square is equal to minus kx minus b dx by dt. This is again the equation, a differential equation for damped oscillations. We are looking at this dx by dt. It is obviously velocity, and the damping action or the damping resistance offered by the liquid is obviously dependent on velocity. This is the equation for damped oscillations. Now simplifying the equation, we must write d2x by dt square plus b by m dx by dt plus k by m x is equal to 0. You please look at this equation. It's a differential form of differential equation for damped oscillations. Here dx by dt term comes from the resistance of the surrounding medium. So how to solve this equation? The solution of this equation is very simple and can be obtained simply through mathematical rules. But here I just write down the solution of this equation. So the solution of this equation is x is equal to, the first part is amplitude. The first part of this must be amplitude. As we know, when the particle oscillates in the medium, the amplitude must decrease with time. So amplitude cannot be constant. Amplitude has to decrease with time, because the energy is continuously being dissipated by the surrounding medium. So what should I write here? So it is something which is a function of time. The amplitude is something which is a function of time, and that too decreasing with time. And from the solution itself, it is an exponential decrease of time. The amplitude is exponential decrease of time. And again, it is simple harmonic because the particle now will oscillate like this. If it is vacuum, it will oscillate like this all the time, without any damping. But if it is in a medium, then it will oscillate like this, and finally it will stop. But now, as we will see, the damping is fast. It will like this. But after some time, the damping decreases, and it will move. It will oscillate back and forth over a longer period of time. But initially the damping is fast, and the rate of damping decreases with time. So here, this amplitude, which is obviously the function of time, and again it is simple harmonic. So here I will write sine of omega t, omega prime I should write, plus phi, because omega I have reserved for free oscillations. So here is omega prime. Omega prime is the frequency of damped oscillations. So here the amplitude can be written as A E minus B by 2mt. If we look at the equation indicates that it is simple harmonic motion, and the simple harmonic motion with what frequency? With the frequency of omega prime. Yes, omega prime is different from the free oscillations. But if we look at this, the amplitude part of the equation, it indicates that the amplitude decreases with time. And the decrease of amplitude with time is simply exponential. If I write it like this, A prime equal to A e raised to power minus B by 2m t is the amplitude of the damped oscillations, which is very clearly decreasing with time and exponentially, and x equal to A prime sine of omega prime t plus phi. This is the equation for damped oscillations. Equation for damped oscillations. As you may have understood that the amplitude, it decreases with time, so does the energy. But the energy is proportional to the square of the amplitude. So the decrease of energy is much faster. The decrease of energy is, the rate of decrease of energy is much faster as compared to the amplitude. If I write down the energy equation, so what should I write? The energy equation is obviously energy E equal to E0 e raised to power minus B by mt. This equation indicates that when the particle starts oscillating, it starts oscillating with energy E0. But with time, energy decreases because of the dissipative property of the medium. And the energy also decreases with time exponentially. But here, from this equation and this equation, it is clear that the rate of decrease of energy is greater than the rate of decrease of amplitude. So from these two equations, it is very clear that the amplitude and energy, they vary at a different rate. The frequency with which the damped oscillations take place is given by the frequency omega prime is root of k by m. Had there been no damping, then omega bar would have been just equal to omega, the frequency of the free oscillations. But here, in case of damping, the frequency with which the particle oscillates back and forth is lesser as compared to the frequency of free oscillations. So it is omega prime root of k by m minus something. What is that something? That must depend upon the damping factors. That must depend upon the viscosity of the medium. That must depend on the properties of the medium. As I can explain, you see, if a particle oscillates in air, it oscillates for a longer period of time and then stops. You see, if the particle oscillates in a liquid, then it oscillates and stops very quickly. If it oscillates in glycerin, then it may oscillate like this. So the viscosity of the medium determines how fast the energy is being dissipated in the medium. So here it is k by m minus b by 2m whole square. So this is the equation for frequency of damped oscillations. Now let us go to the last point, forced oscillations. Forced oscillations. In case of damped oscillations, we know when the particle oscillates back and forth, finally it has to damp down because there is a surrounding medium. So if we have a spring like this, we have a spring and I hold the spring by my hand and pull the mass downwards, attach the mass which is attached to the spring. If I pull it downwards, it will oscillate up and down like this. And this will oscillate in a medium, let me suppose the medium of air, and it will finally stop because of the dissipative properties of the surrounding medium. Now the moment I feel it is oscillations are dying down, I'll push my second hand up and down. So this is what you call as forced oscillations. The energy, the rate at which the body loses energy, I'll supply the energy by the external force at the same rate. So what will happen? This particle will oscillate continuously because I am supplying energy from outside. The rate at which it loses energy should be equal to the rate at which the energy being supplied to the object. So in that case, we call these forced oscillations. And the equation can be written as d2x by dt square plus b by m dx by dt plus k by mx. I would write 0 had it been damped oscillations. But as it is forced oscillations on the right side, I must write down the force. And the force is obviously the function of time. It is a function of time. It is not a constant force. And the simple force function can be sinusoidal. It can be periodic. That is the simplest the force expression that I can write. It is F0 sine omega double prime t. This is the equation for forced oscillations. Again, if I find a solution, the solution is x. It is on the damped part of this solution and the forced part of the solution. The damped part of the solution is already that we have found. That is a e raised to power minus b by 2 mt sine omega prime t plus phi. This is the damped part of the solution plus the forced part of the solution, that is b sine omega double prime t plus delta. This is called as the transient part of the equation. The transient part of the equation will go after some time, and finally this part of the equation remains. X is equal to b sine omega double prime t plus delta. This is the steady state solution. Steady state solution of the equation. Dear students, this was the last lecture on simple harmonic motion that I have delivered. Next time I'll be delivering lectures on different topics. Till then, goodbye.